Hello everyone, I'm Qinqin Cao from Stony Brook University. Welcome to my talk. Today I'm going to talk about our mobile DNN accelerators accelerating DNNs. This is a joint work with many researchers from Samsung AI Center, University of Oxford, and University of Cambridge. As you already know, deep learning applications are becoming more popular today on mobile devices. For example, mobile users can use their smartphones to take photos and then do real-time machine translation. Mobile users can also use Alexa, Google Assistant, or Siri to help their daily tasks. More deep learning applications include face recognition and landmark detection. All these applications can happen on our smartphones. However, challenges still exist when running DNNs on mobile devices. For example, deep learning workloads often consume significant energy, but mobile processors often run on battery-powered mobile devices, like your smartphones. Moreover, running DNNs require large amounts of computation resources, but mobile processors often have limited processing power. For instance, desktop GPUs often has 3 orders of magnitude processing power than a smartphone. Embedded devices, like a microcontroller, even have less computational power. The same also applies to memory. For example, like GPU have 32 gigabytes of memory, but a microcontroller only have a kilobytes of memory. So to make DNNs run more efficiently on mobile platforms, many customized commercial DNN accelerators called XPUs, like VPUs, TPUs, or IPUs, have been developed. So these accelerators often claim to have better energy efficiency than conventional processors like mobile CPUs or GPUs or DSPs. So in this work, we want to ask, are mobile DNN accelerators the real solutions to solve the energy and computation power challenges? So before we talk about the answer, let me introduce a bit of the background of mobile processors in the context of DNN computation. First, mobile CPUs such as ARM processors, as shown in this figure, have many ALUs or arithmetic logic units that perform mathematical operations, which are prevalent in DNNs. So these ALUs have single instruction multiple data or SIMD capabilities to parallelize compute-intensive operations like matrix multiplication. However, CPUs are often designed for more general tasks and have complex control logic and lower compute density, which are mainly optimized for serial control-heavy operations. So in contrast, DNN workloads are very computationally intensive, but have relatively simple coarse-grained control flow. On the other hand, GPUs are designed to accelerate graphics applications, thus having stronger SIMD capabilities built for massive parallel workloads. So in this figure, you can see there are many more ALUs, like small green box. So deep learning execution frameworks can use the GPUs, can utilize these GPU shader cores, which are usually range from hundreds to tens of thousands, to parallelize these mathematical computations. But mobile GPUs often share memory with CPUs, whereas memory accesses are quite energy consuming, because each operation needs to access external GPU memory. Another type of mobile processor is DSP, or digital signal processing processor. So mobile DSPs, for example, like Hexagon DSP on the Qualcomm platform, often use SIMD extensions, which enhance the original SIMD technique by introducing extra vector execution unit in addition to the ALU units as mentioned in the CPU or GPU architecture. So another feature of the DSPs is that they usually support 8-bit integer-based operations instead of 32-bit floating-point operations to further reduce compute cycles, and thus can reduce energy footprints. To do a quick recap, we already know that CPUs are often designed for general-purpose tasks. It also has SIMD instructions for parallel processing. But whereas GPU originally designed for graphics processing, which can support massive parallelism. The drawback is that they are often power hungry. In contrast, DSPs, which are originally designed for photo, video, audio, or this media processing, often have integer-only vector operations, which are more energy efficient. Now, the goal of this work is to understand the DNN performance on mobile accelerators in comparison to the conventional processors like CPU, GPU, and DSP architectures. So in this work, we focus on one class of commodity DNN accelerators called an Intel Neural Compute Stick, or NCS. So Intel Neural Compute Stick is one of the first commercially available accelerators for mobile, wearable, and embedded systems. This Neural Compute Stick is powered by a low-power, high-performance vision processing unit called VPU, which are designed to handle DNN applications. So the architecture difference here between the VPU and mobile CPU or GPU DSP is that it contains a 12 128-bit vector processing cores called Shift processor, which can compute most of the neural network load. So there are two different versions of NCS. NCS version 1 was initially designed to have 12 Shift cores and has a 2 megabytes of on-chip memory. So recall that this memory is different from DRAM, which is SRAM. It's more energy efficient. So NCS version 2 has a more powerful VPU and increased the number of shift cores from 12 to 16. Additionally, it includes a new neural computer engine, which is dedicated for DNN workloads. So both of the two NCS devices aim to accelerate DNN computations with higher efficiency. So why would NCS accelerators matter? Or how these accelerators achieve better energy efficiency for DNN computation? So as you already know, CPUs and GPUs often have SIMD technology, which are essentially the ALUs are performing the computation. But the previous hardware research has shown that for the energy for DNN computation, the bottleneck is actually the memory access in the CPU and the GPUs. So for example, this right figure shows a simple multiply and accumulation operation. And the ALU has to read the DRAM for input data and write results back to the DRAM. So an example DNN like AlexNet has over 700 million of such data movement operations, which consumes most of the energy in DNN workloads. Now for DNN accelerators, the key is to reduce the data movement in memory. So most of the accelerators have local memory hierarchy in the ALU compute unit. So this extra memory can reduce the memory access, like loading model weights and reducing the writing data back to the memory. For example, this local memory can cache and reuse CNN filters and feature maps, which means there's no need to repeatedly perform memory reads. So due to this extra local memory, saving the intermediate computation results does not have to access energy-intensive DRAMs. As a result, a sample DNN accelerator looks like the one in the right figure. So for each processing unit, the ALU has a local memory hierarchy, which reduces the access to external memory. All this memory hierarchy together makes the DNN accelerator much faster and more energy efficient. So DNN accelerators like NCS devices should run faster since they have stronger computational power. For example, this table summarizes the compute capability and the memory bandwidth together with the power consumption. As you can see, NCS devices have 4 gigabytes of operations per second, which is much higher than the mobile CPU or GPU and DSPs. And power consumption is also around 1 watt. In comparison, the mobile GPU or CPU and DSP power on Qualcomm Snapdragon SoC is around 5 watts. So to quantify the performance and power of DNNs, we benchmark 3 sets of hardware devices: Android smartphone, which has all the mobile CPU and GPU and DSPs, the 2 neural compute stick, NCS1 and NCS2. So to support more DNN workloads, for example, to run the NLP models, we use Jetson TX2 board, which has a CUDA-enabled GPU. For the software stack, we use a standard OpenVINO SDK for the NCS devices. We choose the best possible software framework for the DNN execution. So we use TensorFlow Lite for CPU and Snapdragon neural processing engine for the GPU and DSP. To measure the power, we use the Monsoon power monitor for the mobile CPU, GPU, and DSP. And then we use another MakerHawk USB power monitor for the NCS. Since the Jetson TX2 board already has an onboard power monitor, we just directly use that. So the right figure shows the example setup of these experiments. We use 2 sets of DNN workloads. The first one includes 4 popular DNNs: SqueezeNet, MobileNet version 2, ResNet 50, and Inception v3. The second category are 4 NLP models, which are transformer-based BERT models: BERT Tiny, BERT Mini, and BERT Small, and BERT Medium. So when we measure we also measure the inference latency and energy on these platforms for all the workloads. We average across 10 runs. Importantly, we scale the voltage and current measurements on different power monitors so that they are comparable. So this figure shows the results for CNN inference latency on these 5 processors. As you can see, the x-axis is the network and y-axis is the latency. The higher the worse. So you can clearly see NCS version 1 is much slower than GPU and DSP. This is likely because the reason that the NCS2 abandoned the shift course, because they are not optimized for CNNs, as you can see from the NCS1. And instead, NCS2 adopted a new dedicated neural computer engine, specifically for these CNNs. This is also reflected in the measurements. So NCS2 consistently beats this NCS1 as expected, and is often faster than GPUs as well. However, DSP is still the fastest accelerator for all the CNNs in our study. So as for the energy, you can clearly see that this figure shows the consumption of the 5 processors. So the NCS1 and 2 consumes more energy than the GPU, but much less than the CPU in our cases. This is kind of surprising because mobile accelerators like NCS1 and NCS2 are designed to run the CNNs in a more energy-efficient way due to a specialized chip design. Conventional mobile processors like GPU and DSP are the winners, so compared to the NCS accelerators in both latency and energy efficiency. So to understand why these CNNs are slower on the NCS than the GPU and DSP, we perform a Roofline analysis. So Roofline basically plots and compares the performance of different kinds of processors. We can easily analyze processor bottlenecks for given workloads, so either they are compute or memory bound. So basically, this plot on the x-axis shows the operational intensity. So the y-axis just shows the peak performance. So when the workload intersects the roofline in the slope, then we can see it's a memory bound. And when the workload intersects the horizontal line, then we can see it's a compute bound. So for the NCS accelerators, we can see they are mostly memory bound due to limited available memory, except for the SqueezeNet, which is a very small network. So this means for all the studied CNNs, except the SqueezeNet, they cannot fit into the NCS memory. Even the accelerator has better local memory architecture. In that case, even more prioritization does not help, because the workload is memory bound. So what if we can't, since we can't change this hardware easily, what if we change the model parameters? We can change some parameters to see how the NCS, where the NCS can help. So we try to vary the CNN filter size and the number of filters, basically the network depth, and the number of layers, basically the network depth. So the number of filters and network width. So I'm going to show the effect of changing filter size versus the network depth. Specifically, we vary the filter depth of common 1x1 or 3x3 and 5x5 filters to investigate the impact on latency for an NCS2 accelerator. So as we increase the filter depth, we observe abrupt increases in latency at specific depths. We call this vectorization effects, as they are likely due to the filter size exceeds the vector instruction paradigm in the NCS2. So NCS2 has to issue another vector instruction to complete the computation. So for example, if the vector weight is 16 for multiply and accumulate instructions, and we have 17 such max in our filter, then two vector instructions will be needed. The first one is fully utilized, but the second one will be underutilized. That's why we can see such abrupt increase in latency. But we also see that other devices such as CPU or GPU has much finer grained paradigm, so we don't see such effect on the device. So our focus is on these specific properties on the NCS2 platform. The NCS2 is very important to study because it is indicative of future dedicated accelerators for DNNs. So we recommend the careful design of DNNs to align to this to take advantage of such vectorization effects in DNN accelerators. For example, in this work, we try to exploit this feature. Basically, what we do is that we decrease the output filter depth in the inception network version 3 to the closest power of 2 and then retrain the model. So you can see this optimized model is more like a pruned model for the NCS2. So this paper summarizes the latency and power results before and after this NCS-aware optimization. You can clearly see NCS2 becomes 15% faster than DSP after this pruning optimization, even though it was 3% before pruning. We also benchmarked NLP models on NCS1 and NCS2 devices. So due to smartphone software limitations running NLP models, we use an NVIDIA Jetson TX2 board for CPU and GPU testing. So for all the four models, you can clearly see that NCS1 and NCS2 are 5 times slower than the CPU and 20 times slower than the GPU. So we hypothesize that the NCS accelerators are not optimized for NLP models like BERT. The reason is that BERT models often use attention mechanisms, which has different properties compared to CNNs. For example, CNN models often have filters that are easily parallelizable and can be cached into device memory. But attention-based NLP models often need to look at all the input data at once and cannot easily fit into memory. We also have the energy data in the paper. The results are similar. Basically, the NCS devices consume more energy than CPU and GPUs. So all these DNN workloads results are preliminary. And we show that this NCS device latency and energy behaviors. So to understand the reason why NCS are not good alternatives to conventional processors like GPUs and DSPs, further investigation are needed. To summarize, this work shows the first set of results, basically the performance characterization of DNNs on commodity mobile DNN accelerators, NCS1 and NCS2. We also show how we can change the model parameters so that we can better utilize the features of these hardware accelerators so that they can take advantage of this processor design. One important thing we notice that mobile DNN accelerators are not ready yet to support to accelerate DNNs. And they are just like conventional mobile processors. They are only as good as if their software and algorithms drive them. Thank you.